Section 7.3, the definite integral. So in the last class we saw that we could approximate area using something called Riemann sums. These Riemann sums were basically rectangles that were stacked together to approximate an area, and we use sigma notation to represent the sum of those rectangles. Here in our formula, this f of x sub k, that represents the height of all the rectangles. The delta x represents the width of all the rectangles. And when you multiply those together, you get the area of each rectangle and add them up. And that is our approximation. Here, the number n represents the number of rectangles that we use, and we could use few or many. X sub k represents the x value at which the heights are determined. And there's different ways that we could choose those. For instance, in class we saw that we could do a left-hand sum. So if on our first rectangle here we had determined the height on the left side, then we would have a red rectangle. If we had determined the height on the right endpoint, then maybe instead we would have had the purple rectangle as our first rectangle. In this particular example, it looks like they're maybe using a midpoint sum or something of the sort. So it looks like they maybe picked an x value that was about here, and therefore they ended up with the height up to exactly this point, and that's why they used that rectangle. But in any case, the height of each of these rectangles is determined by an x value in each interval that is then plugged into the function. Okay, so that x value is plugged into the function, and that point on the function then determines the height of each of those rectangles. In particular, we saw that right-hand sums, the x values followed a linear progression, and so we would use x1, x2, x3, all the way up to the last xn, and that we could write a formula for these because they formed a linear progression. So sometimes if we're writing Riemann sums with sigma notation, it's helpful to know that formula. The delta x here also represents the width of each rectangle, and that can be calculated by just taking the width of the interval. So here A is the left endpoint and B is the right endpoint, and subtracting those and dividing by n, and that's how we can calculate a uniform partition of that interval. Keep in mind that we can always improve approximations by increasing how many rectangles we use for that Riemann sum. So, now that we know that, it's time for the definition of a definite integral. So, given our summation here, so this here was our symbol for the Riemann sum, and since we can improve this approximation by increasing the number of rectangles, what happens if we take the limit as n goes to infinity? So in other words, as we allow ourselves to use more and more and more rectangles, well, that limit is exactly what we call the area. Okay? And so no more error, no more approximation, it is exactly the area. And our symbol for that looks similar to this, only that instead of a pointy S, which sigma is, it's got these jagged pointy corners here, we'll use a smoother S, and the function is still part of our formula, and this delta x, so because we're using more and more rectangles, what's happening is that delta x is getting smaller and smaller. It's almost going to 0. And so to indicate that, we'll use a dx instead of a delta x. So this is our symbol for the area. And it's called the definite integral. You can read this symbol by saying it's the integral from a to b of f of x. You can also say that it's the area below the graph of f. So if you look up at the picture, you'll see that so we have the graph of this function f of x right here. And we're looking at the area between that graph and the x-axis. And the a and the b here give us then a left margin and a right margin. And so the area that we're talking about is trapped between those four boundaries. As long as this limit exists, or this area is finite, we say that function f is integrable on that interval. So, let's try a few properties. The first thing that you should keep in mind is that the definite integral should be thought of as area. Okay, so don't be confused by the symbols and all the squigglies and the dx's and all that. Keep in mind that we're talking about area. So in this first integral, what are we talking about? Well, we're talking about the area below the graph of 3. Okay, so there's y equals 3. Between 2, so here's 2, and 5. Here's 5, so that's another boundary. And above the x-axis. So this is the area here that we're talking about. So do you know how to find that area? Well, it's a square. It's also a rectangle. And if you know how to calculate length times width, 3 times 3, then the answer is 9. And that's it. That's all there is. In the second integral, we have a little bit more to do. This is a line, so think of it as the graph of a line. The y-intercept is 3, and the slope is -1. So you can imagine here our line with slope -1, and the graph of that kind of goes like this. Okay? And we're trying to find the area below that graph and above the x-axis, and with a left margin at 0 and a right margin at 2. Okay, so now we're talking about this area right here. Well, so one thing you could do is just eyeball it, right? So you could say how many squares are in there. So you could count 1, 2, 3, and then maybe this is a half and this is a half. So the answer should be 4, right? Although counting squares isn't always the best method. And so in this case, it would be helpful to recognize this as a trapezoid. This is a right trapezoid. And you might remember the formula for the area of a trapezoid is 1/2 height times the sum of the bases. The bases being the parallel sides here. Which actually this trapezoid is kind of turned on its side, right? Because this is actually the height, and then this is base 1 and base 2. Okay, so if I was using this formula, I would say that the area is 1/2 times, and the height is 2, and then base 1 is 1, and base 2 is 3. Okay? And if you evaluate that, then of course you get 4. Okay, so that would be using the shape of a trapezoid in geometry. The third example here might look unfamiliar to you. And you might say, well, whoa, what is that? And so I'll fill you in. That's the equation for a circle. You might remember at some point learning a formula like this one, x squared plus y squared equals r squared, and that kind of looks like the Pythagorean theorem. It's actually the equation for a circle here where x and y are the coordinates of the points, and here r is the radius of the circle. Okay, so the radius. So how does that turn into that square root looking thingy? Well, if we flip the x squared to the other side and then take the square root of both sides, right? So we take the square root and we get y equals r minus x, and wrong, wait a minute. You can't square root r squared minus x squared like that. Oh no. We need to leave it in the square root symbol. Okay, that would be a wrong simplification. So now you can see that this here looks exactly like this right here. And so this happens to just be a circle with radius. What is the radius? Is it 9? No, it's 3. Okay, because that's r squared. Right there, that's r squared. So 9 is r squared. So the radius is the square root of 9. Okay. So what we're looking at here is a circle with radius 3. And so I'm going to do my best to draw it here. So here's a circle with radius 3, and there's more to it, but we're only interested in the part of this that's above the x-axis, and with 0 as a left boundary, and with 3 as a right boundary. So if we're looking for this area right here, well, the formula for the area of a circle is, of course, pi r squared, and since that's a fourth of a circle, then we have 1/4 pi r squared. And so plugging in the 3 for r gives me 9 pi over 4. 9 pi over 4, and it's fine to leave it like that. Otherwise, if you type it into your calculator, you'll get some nasty decimal. The second property about integrals is this partitioning property. And I hope this is very intuitive to you once we start looking at it. But basically, it's the idea that if a definite integral represents an area, then you should be able to split up a larger area into smaller areas. Okay? And so if you pay attention to the limits here of these integrals, the first integral here is the integral from a to b. Okay? So a to b. And so notice that we're talking about this whole area right here, all of the colored part. Okay? So that entire area is equal to, so what is it equal to? It's equal to the integral from a to c. So where's c? So the integral from a to c, okay, that would be the yellow section, plus the integral from, let's see what color do I pick, green, from c to b. And where's c to b? So c starts where the first one left off and concludes that interval. So in other words, the whole shaded area is the sum of number 1 plus number 2. Okay? So it's just a matter of dividing that whole area into two smaller areas. Makes sense, right? Here's an example. Suppose that the integral from 0 to 5 is 12 of, so some function f here, we don't even know what that function is, but it doesn't matter. And the integral from 0 to 3 of that same function is 4. So, if we know those two things, what is the area from 3 to 5 of that same function? Okay, so if you need to, let's sort of envision what this means. So here's 5, here's 3, and so the first statement says that the area of this whole section here is 12. Okay, so from 0 from 0 to 5 is 12. But we're also told that the area from 0 to 3, so this area right here, is actually 4. So I did not draw my picture to scale. Okay, so the whole region from 0 to 5 is 12, but the region from 0 to 3 is only 4. And the question is, what's the area of the region from 3 to 5? So this from 3 to 5, what is this? Okay, well, so the answer would be that you would take the area from 0 to 5, the 12, and you would subtract the area from 0 to 3. Alright, makes sense? And of course that gives us 8. Third property of integrals. I call this the linearity property, or that we say that the definite integral is a linear operator. What that means is that if you have an integral with some complicated looking stuff, okay, in particular I'm referring to here addition or subtraction, that's an arrow, addition or subtraction, or I'm also talking about coefficients, okay, so there's some number c multiplied by f of x, some number d multiplied by g of x. Then what we can do is we can simplify, or we can split up this larger integral into smaller ones. And for one thing, this plus can separate this larger integral into two smaller ones. So we can write this as two separate integrals on the same interval. But also these coefficients, so the c and the d, can also be taken out of the integral and multiplied by the area afterwards. Okay, so let me show you an example. So suppose that the integral from 1 to 5 of f of x is 7, and the integral from 1 to 5 of g of x is 4. So we have two different functions, but on the same interval. And we want to evaluate the integral from 1 to 5 of twice f of x minus g of x. So, based on the property of linearity, what we can do is we can rewrite that larger integral as two separate ones. And so the minus here is what separates them. And I also pulled out this 2 outside of the integral and put it out here in front. And since I know what those integrals are individually, so I know that the integral from 1 to 5 of f is 7. Okay, so this part right here is 7. And since I know that this integral, the integral from 1 to 5 of g, is 4, then I can just substitute those in, and I get an area of 10. Fourth property. So, even though we think of area generally as a positive quantity, in the definite integral, there is a way for area to be negative. So let me explain. The first way that we can see this happen is that area below the x-axis is negative. Okay, so how can this happen? I thought we were always looking for area between the graph and the x-axis. Well, that's true, but what if the function is below the x-axis? Okay, so take a look at this picture, and here you'll notice that this function is partly above the x-axis, is partly below. And so the area that's above the x-axis will count as positive area. The area that's below the x-axis will count as negative area. So you say, well, why is that? Isn't all area positive? And the answer is, well, sure, but it's because if we were to approximate this area with a Riemann sum, right? So imagine that we're using rectangles whose height is determined by the function. Right, and so we fill these in, and so far we have positive area because all of our rectangles here have positive height. But so what happens though once we get to here? Well, once we start getting into the region where the function is below the x-axis, what happens is that the heights of the rectangles, okay, become negative. And when you multiply a negative height by a positive width, you get a negative area. For example, here we have three integrals, and the rule for all of those is x minus 4. Okay, so the y-intercept is at negative 4, and the slope is 1, and we have three different integrals. So the first one is the integral from 0 to 4. So our left boundary is 0, our right boundary is at 4, and we want to find the area between the graph and the x-axis. So this area right in here. So of course you can count squares. You can also use the area of a triangle formula, right? And so that triangle happens to have base and height are both 4. So 4 times 4 is 16. Divided by 2 is 8. But because the area is all below the x-axis, then our answer is going to be negative 8. On the other hand, the area that is from 4 to 6, so here's 6, so 4 to 6 is here, and there's the x-axis as our boundary, so this area is above the x-axis. And again, if I use my triangle area formula, 2 times 2 is 4, divided by 2 is 2, and this time this area is positive because it's above the x-axis. So what if part of the area is above and part is below? So what about the integral from 0 to 6? Okay, so now I'm talking about all of this area combined with all of this area. Well, I'm sure you can guess that it's just the sum of the two. And since part of it is below and part of it is above, the answer is just the difference. And so the combined area is negative 6. So that's one way that we can have a negative value for a definite integral, which you can think of as negative area. And that would be by having the rectangles have negative height. But there's one more way to get negative area, and that would be by having negative width for our rectangles. So this is a little different, and the width of the rectangles, remember, is delta x. Okay, and so delta x was how wide our rectangles were. And if you remember, the delta x was calculated by doing b minus a over n. And as long as b is bigger than a, right, so as long as b is on the right and a is on the left, this should come out as a positive quantity, right? It should come out as greater than 0. But what if a happened to be larger than b? Well, then that would come out as negative, and therefore the areas would come out as negative as well. So when does this happen? When does a happen to be bigger than b? Well, sometimes when we write a definite integral, we might write the limits, okay, so the upper and lower numbers, we might write them out of order. Don't worry, it's an easy fix, because if I happen to have these numbers out of order, I can just swap them. Okay, I can just change their order, as long as I keep in mind that I have the opposite sign, because I had a negative delta x and I really wanted it to be positive. Okay.